Yes, welcome everybody to our row this week. So I'm very happy to introduce Marc Goerigk. He's a full professor at the University of Passau, and possibly you know his name. He published an incredible amount of papers, especially in the field of robust combinatorial optimization, but also robust operation research and data-driven optimization. And recently, I have to mention that the Wirtschaftswoche, which is a German economy newspaper, elected him under the top 50 most influential German business economists, and even under the top 10 in the category of an age below 40. So thank you to be here, and the floor is yours.
Thank you, Janus. Yeah, thank you for the very kind introduction. And it's a great pleasure to be speaking again at the Robust Optimization webinar. And I'm really grateful that you two have started reorganizing this. So I've been enjoying the previous presentations, and I'm sure I will enjoy the next presentations as well. So let's hope that this in between is not an outlier, but let's see. So this is a topic that I really enjoy talking about. And of course, that's not necessarily correlated to you enjoying hearing about it, but I try to do my best. Let's see. So what is this about? Now you just need the focus here. Okay, right. So if we're talking about robust optimization problems, we usually add some kind of layer of complexity to our problem. I mean, sometimes it may seem like you remain in the same complexity class, which is nice, but if you actually have to solve it, nearly always it's the case that solving your robust problem will be harder than solving a nominal problem that doesn't have any uncertainty. A rare exception is perhaps if you have interval uncertainty sets, because then if you think about the 0-1 word, the worst case is always the upper corner of your box. So your robust problem is just the same as a nominal problem, but then you lose a lot of flexibility in designing reasonable good uncertainty sets. So you can't even capture anything like correlation in your data. So you usually want something that's a bit more complicated than that. Now, the number of scenarios, if you think about discrete uncertainty sets, is like the most important factor that drives up the complexity when you want to solve your problem. So here's a small example. I've solved like a selection problem where I vary the number of scenarios. So this is a very easy one-stage problem. The case for one scenario is even solvable in polynomial time. And as you increase the number of scenarios, the problem tends to get harder quite dramatically. Okay, so the question is, do we really need all of these scenarios? Or perhaps if we have like 100 scenarios, like in this example, maybe we can throw some of these scenarios away. So we have a reduced uncertainty set, or maybe we can combine some of these scenarios together. So if you have 100 scenarios, you could just use something like k-means clustering on these 100 scenarios, and you get a smaller uncertainty set. Maybe you just end up with 5 scenarios. So that's what I did in this example. I went down to 5 scenarios. And then, of course, aggregating and solving your problem is this orange line. That's much, much faster. But what can you say about the quality of this? And this k-means really the best thing you can do here, because k-means cluster similar scenarios together. That's fine. But it doesn't necessarily have the outlook that you cluster them together because you want to solve a robust optimization problem afterwards. So maybe the part of information which is important for your robust problem is getting lost in the process. So maybe you can do something better, something more specifically tailored for robust optimization.
Marc, sorry to interrupt. I think your slides are cut on the right and the left. So we,
oh no,
I at least don't see it completely.
Okay.
Okay, maybe just reshare.
I would try. Yeah. So can you see better now?
Now it's better, yes.
Okay, so I went out of full screen mode, and I would just try to do it like this. So ignore the Windows decorations around that. Okay, thanks for letting me know, Janus. And by the way, if you have any questions, of course, we've got time for questions in the end. But if it's something that's helpful to answer right away, then just please do ask. Okay, so I'd like to have something that reduces the number of scenarios for my optimization problem. So I'm looking at like very simple optimization problems. So let's say you start with a nominal problem, you've got some feasible set of solutions, and you have a linear objective function. So just a scalar product between your costs and your decisions. Now, if you apply robust optimization to this, you will have some uncertainty which may affect your constraints. So you've got a different set of feasible solutions for every scenario, and you may have different costs in your problem for every scenario. Now, for the purpose of this talk, I would like to ignore this kind of uncertainty in the constraints, because if you aggregate your scenarios down from 100 down to 5, and you end up with something which is infeasible, well, that's bad, of course. So aggregating down is, I think, very dangerous if it's about feasibility. And also, because I like thinking about the combinatorial world, there it's much more common that you say you've got some underlying structure like a graph or whatever, and usually that's not affected by uncertainty. Instead, you say the costs are affected by uncertainty. So let's focus on that for the purpose of this talk. But aggregating scenarios and keeping feasibility might also be very interesting to do. Okay, so my kind of robust optimization problem that I would like to focus on in this talk is that you make some decision. So think about it as a 0-1 decision, but nothing in this talk is actually restricted to 0-1 decisions. It could be anything. And then the adversary chooses the cost factor, and you have to pay for that. Okay, so a question is always how to model the uncertainty set, the shape of the uncertainty, right? There are different options there available. And the shape of the uncertainty very much influences the complexity of the problem. So as I already said, if you've got an interval set, it's a very easy problem. If you have something like a budgeted uncertainty set, you've got more flexibility and you remain polynomially solvable if you start with something that's polynomially solvable. But so what I would like to look at here are discrete uncertainty sets. And I think one of the main motivations for that is that this is a very natural description of what may happen, and that may even come from the historic data right away. So most of the time when we talk about historic data, we actually have some measurements available of what happened in the past. So let's say we've got these n measurements, and one very important specialty of what I'd like to talk about is that this is all non-negative, because this can have a big impact on what is the worst case if your decision variables are also non-negative. Okay, so let's focus on this discrete uncertainty sets where we start out with n observations of the past. Now, this is nice from a modeling perspective, I would say, but of course, these problems tend to be very hard, very much right away. So if you look at like a standard shortest path problem, like as a standard way of formulating a combinatorial optimization problem, you've got given a graph and you want to find the shortest route from S to T. Now, if you only have one scenario, this is a very easy problem. So if you just have one scenario, you can use something like Dijkstra's algorithm. And so this is strongly polynomial. And even for very large graphs, you can solve this very, very quickly. Now, if you just have one more scenario, so let's say you're not quite sure if you're using a path in the morning or in the evening, so maybe there are two possible cost realizations, already then this very simple problem becomes NP hard. And this is something which is not like specific for shortest paths. I mean, every reasonable 0-1 optimization problem, if you have two scenarios, suddenly becomes NP hard, because suddenly you have this balancing aspect in your problem. You have to balance the maximum of two scenarios against each other. So whenever you've got something that you want to put into balance, but it's discrete, it tends to be NP hard. So already for two scenarios, that's hard, but that's not the end of the story, of course. I mean, for 3 scenarios, it's in the same complexity class, but it will be harder to be solved in practice. And what you can also see from a theoretical perspective is that if you have n scenarios, you cannot approximate better than log n. So this even gives you an upper bound, a lower bound on the kind of quality of solutions you might be able to achieve in polynomial time, of course. Whereas if you have a constant number of scenarios, there's even an F-Peters for shortest path problems. So basically, there's a difference between having 2 or 3 scenarios or many scenarios, which is another motivation why it might make sense to take something where you have 100 scenarios and you want to go down to 4 or 5, which means that you're in an area where the problems are easier to solve, even though they are NP hard. Okay, but yeah, as we've often heard, I mean, even if something is NP hard, that doesn't mean that it's not solvable. Okay, so let's focus first on this one-stage robust optimization case, and then I will also talk a bit about the two-stage case. And in both cases, there are some like principled ways to do an aggregation so that you even get some approximation guarantee out of this. Okay, so let's start with a one-stage case, and we want to go down to one single scenario. So I've got 100 scenarios. I just want to go down to one. And of course, going down to one scenario can be very practically relevant because one scenario problems may be easy, whereas two scenarios are hard. So in the literature, there are already two methods to do that, which are have been well known for I don't know, 15, 14 years. So the first one is the midpoint or the average. So you've got n scenarios, and you just take the average case of these n scenarios. And in fact, that is an n approximation, meaning that if you go down to this one average case scenario, you solve it, you get some solution, and you take the solution back to the original problem. The objective value of this solution is at most n times the optimal objective value. And this is a guarantee that you get before even solving the problem, right? So before I even start, I know it's at most factor n away from the optimum. But factor n, I mean, it's nice that we can bound it, but factor n is not a very good bound, obviously. And there's an alternative method, which is the element-wise worst case. So in this case, you may have plenty of scenarios, and your average will be just the one scenario in the middle. And here, the element-wise worst case would mean that in this two-dimensional example, you would always look at a single component, what is the worst case in that component, and construct a scenario like that. So essentially, that's the upper corner of all the points in your uncertainty set. Okay, and this also gives you an n approximation. Okay, so the question is now, given a number of scenarios, can you do better than this? And to understand that, let's look at the proof first. Why is this an n approximation? And so for both variants, let's look at the midpoint solution, the average case. There's a very simple proof. In fact, it's so simple that I would like to go through this line by line. Because let's say you solve it with your average scenario, and that's now x hat, that's your solution. And there's some x star, which you don't know, obviously. Now, if you calculate the robust objective value of this average case solution, so you've averaged the scenarios, solved that, and plugged that back into your original problem, what is the objective value of that? Well, the maximum over all scenarios is certainly smaller than the sum of all scenarios. And here it's important that we have non-negativity in our uncertainty set, otherwise that wouldn't be true. Okay, the maximum is smaller than the sum, and the sum of all scenarios is of course nothing but n times the average of all scenarios. So you get that your maximum is smaller than n times your average objective value. Okay, now the solution x hat is exactly the one which is the best for scenario c hat. That's how you optimize that. So you know that it's even better than the solution x star, whatever that solution might be, for this specific scenario c hat. So you get this estimate, and now you go back. So c hat is something which is in the convex hull of all scenarios. So it's certainly smaller than the maximum in the convex hull. And the maximum in the convex hull is the same as the maximum over all the extreme points because we have this linear objective function. Okay, so this is why we get an n approximation guarantee. And now I've been going through this proof in great detail because this basically gives you the ingredients how to make it better. So we only need two estimates in this proof. So the first is we have to do something which is in the convex hull. So being in the convex hull allows you to do this estimate down here. And the second ingredient is that we want to have something where for every possible scenario, we can bound it from above by multiplying with some factor z. And we've done that in the previous case here by saying that this is smaller than n times our scenario. Right? So this is the two ingredients that we need. Now, if you have a scenario like that in the convex hull and every scenario is less or equal to z times this scenario, then you have a z approximation using exactly the same proof. But now you can try and formulate this as a linear optimization problem, right? So we move the z from the right-hand side to the left-hand side because I don't want the non-linearity here between my variable and my scenario. And now I can just maximize instead of minimizing, right? So the variable t is now essentially just the 1 over z. I maximize t so that this is fulfilled and I have a convex combination of the existing scenarios. And now I know that if I solve this LP, the solution will be something which is a 1 over t approximation. And I already know before solving this that this factor 1 over t will be better than factor n because this would always be a feasible solution in this linear optimization problem, plugging in your average case scenario. But I know that it will be never worse than that. Okay, now this is something that I started out with a couple of years ago, and we recently picked it up again and started to think about how can we extend this to multiple scenarios and not just one. And now a first way to generalize this is that you could say you don't necessarily require something that comes from the convex hull itself. Instead, for every there is an element in the convex hull which dominates your aggregated scenario by factor beta. And if you have this, you have a factor alpha times factor beta using the kind of same proof as before. Now, how does this help me? It means that I can pick any scenario, and now for this scenario, calculate what is the approximation guarantee that is implied by this scenario, even if it's not in the convex hull, which means that this also captures the kind of the element-wise worst case. And the proof is essentially the very much the same as before. So you can upper bound your scenario by this beta times scenario, which comes from the convex hull. And then the rest goes through as before. And now this allows us to plot something like the approximation guarantee in a small two-dimensional example. So here I've just got two scenarios. So the first one is 4, 2 over here. The second one is 2, 3 over here. So these are the two scenarios. And now the color indicates that if I just solve with a scenario which is placed at this point in this 2D graph, this is the guarantee that I will get for my solution. And we're not talking about even what kind of optimization problem I have. This is completely independent of the optimization problem you have, whatever that might be, knapsack or shortest path or whatever you wish for. Okay, and one thing which I think is very nice, but you can probably find it hard to see in the screen, is that the level sets are actually straight lines. And this is because if you have a solution to one scenario and you just scale that scenario up by a factor 100, you still get the same solution, right? And this means that you still get the same approximation guarantee. Okay, and so this is something we have to keep in mind when we think about approximating our uncertainty set. I mean, k-means will try to do something here in the middle, but actually you could just scale it up or down as much as you like, and you would get the same solution, and you should get the same approximation guarantee. And here the best case would be to just go here through the middle between these two scenarios, and that gives you an approximation guarantee of 1.25 in this case, whatever problem you want to solve. Okay, now, this is something I can do for single scenarios, but now I want to go up to multiple scenarios. The reason is that, of course, that if I have more scenarios, I can hope for better approximation guarantees even before I solve my problem. So solving the problem with more scenarios will be harder, obviously, but I can hope that the solution will be better. So let's say I start out with an uncertainty set of n scenarios, and I would like to go down to k scenarios. And now I can do the same kind of alpha beta thing as I've just showed for a single scenario. So for each of the original scenarios, there must be something in the convex hull of my scenario so that I can upper bound that scenario, right? So I want my scenarios to be large, essentially. And for each of my original scenarios, I want something from the convex hull which upper bounds my scenarios. Okay, so this is this vice versa relationship between the two polytopes. So you've got one polytope, the other polytope, and you always want to be able to scale one up so that it dominates the other one, essentially. And if you have that, then you get an alpha times beta approximation. Okay, so how can we find these? Well, I mean, it's nice that I can say, given any k points, I can calculate this alpha and beta. And that even means that if I run something like k-means, I can now go to this result and calculate the approximation guarantee of my clustered scenarios without even looking at the optimization problem, but just calculating these alpha and beta values, which is straightforward to do. But what I would like to have is something which gives me the best guarantee. So I'm trying to formulate this again as an optimization problem. And now this is kind of similar to the thing that you've just seen. It's just getting a bit more complex because the k scenarios you would like to have are now given through these lambda ki variables, which means that for your k scenario, this is the convex combination of the existing scenarios, right? So for each of your k scenarios, you have a convex combination constraint here, right? And so this part gives you your ck. And now for the other constraint, we want something that dominates, if we take the convex hull of our ck scenarios, the original ci scenarios. So I have a convex hull of the original ones. I go down to k, and now I can take the convex hull of these K scenarios, and I want to find something in this convex hull of the K scenarios which dominates my original scenarios. That's the kind of double step thinking you have to do there. Okay, so we've got another set of convex combination variables here, which means how do I take the convex combination of my K scenarios so that I dominate everything from my original size scenarios. Okay, now this is unfortunately non-linear now, because we have the product here between the mu's and the lambdas. Everything else here in this constraints, the CI's, CL's, that's all the given data. Okay, and one way you can think about this is that what's going on here on the right-hand side is a bit like a matrix multiplication. So you've got your mu matrix and you've got your lambda matrix, and the mu matrix is of dimension n times k, and the lambda matrix of dimension k times n. And so if you multiply them together, what you want to have is something which is close to the original data. So you're going down to k and going up to n again. Of course, having these constraints for this convex combination, which means like the rows in these matrices are normalized to 1, and being as close as possible in the sense of dominating is fine. You just don't want to be smaller. Okay, so this is like a non-linear optimization problem, but this is hard to solve. There are nowadays solvers where you can just plug in this non-linear problem like Goerigk, and we tried that, but even for very small problems, that was completely hopeless. Okay, but any feasible solution now gives you some kind of approximation guarantee. So it's okay if we don't solve it to complete optimality. Anything along the way will be helpful. And so what you get out of this will be a 1/t approximation again. Now, this problem is in fact not just computationally challenging, it's also NP hard. And so, well, I don't want to show the full NP completeness proof here, but just to give you an idea why this could be the case. So this is hard, and to see that, let's start from dominating set. So in dominating set, you've given a graph, and you want to choose a subset of nodes, so that for every node in the graph, you've either chosen the node itself into your set, or you've chosen one of the neighbors. Okay, so it's a bit like vertex cover, but you don't want to cover the edges, you want to cover the neighbors. Okay, so let's start with this very simple dominating set example here. So you've got these 3 nodes, so obviously the best dominating set is picking V2 because it dominates the 2 neighbors, and you're done. And now the question is, if there's a cardinality K in your dominating set, and I claim that this is the case if and only if you can find some scenarios which give you a 4/3 approximation guarantee. And so to build these scenarios from this small graph, what I do is the following. I have 2 types of scenarios for every node. So one type is the C tilde type, just has a high number that you have to cover in this cost component. So you've got the dimension of these vectors is the same as the dimension of vertices. So 3 in this case. So this has a 16 because it corresponds to V1. This has a 16 here because it corresponds to V2, and a 16 here because it corresponds to V3. Now, what we can show is that actually, if you want to choose a subset of these scenarios, you can choose something in the convex hull, but it makes sense that you just choose a subset of these scenarios. And again, if you want to cover the other scenarios, it makes sense not to do the convex hull of your subset, but you would just cover them one-on-one. So this is something we have to show, but it's something that's possible. So the question is, what kind of subset should you choose now of K scenarios so that you cover everything within a factor of 4/3? And let's say I try to use now C tilde 1 and C tilde 3. Now I've covered C tilde 1, I've covered C tilde 3, but I haven't covered anything else because of the zeros anywhere. So these tilde things are nothing that you can actually pick in your reduced uncertainty set. You have to pick something from the other scenarios because they will have values which are non-zero in each component. And the values that they have is 12 for everything which is the node itself or its neighbor, and 9 for the whole rest. Now, if I pick C1 and C3, for example, then I see that I can cover everything, but the factor that I need is larger than 4/3, because the scenario C tilde 2 has a value of 16, and to go up to 16, oh, well, no, that's fine. So I can cover everything with 4/3. But this uses 2 scenarios. So the question is, can I do it with 1 scenario? Because the dominating set has a cardinality of 1. And yes, I can just pick C2, because that dominates everything within a factor 4/3, right? If you scale C2 up with a factor 4/3, you get 16 everywhere, so everything is dominated in the original data. And so this choosing a subset of scenarios is very closely related to dominating everything else. Okay, we want to choose a subset of scenarios which dominate things. So this has this NP hard dominating set component in this. Okay, how can we solve this? Well, this is a difficult problem, as I say. So one way would be that you take binary variables for mu. That simplifies your problem. You take binary variables for lambda. Again, this simplifies problem. Or you try to do it iteratively. So let's look at these three versions. If you have binary variables mu, so what is the purpose of mu again? The purpose of mu is that you choose which of your subset of scenarios, which of your case scenarios dominates the original scenario. So for every original scenario, you have to pick one in the convex hull, which dominates the original. And now we're saying we're not picking from the convex hull, but we have to have one of the case scenarios which dominates me. So I can now find a better formulation, essentially using constraints like this in the big M sense, where you say, okay, if I want to dominate scenario Ci with Ck, then this has to be active. Now, the other direction is if these lambda variables are binary, that means that you have to choose a discrete subset of these N scenarios. Right, so you can't mix the scenarios again. You have to choose a subset of cardinality K, but because the mu is now continuous, you can use a convex hull of these to dominate the original N scenarios. And again, you can find a nicer way to formulate this, because now you can just have variables which tell you, I use this scenario, yes or no, and this gives you a more effective IP formulation. And of course, the last possibility is that you do an iterative, like a block descent method, where you say, first fix the one part of the variables, optimize for the rest, and then you repeat. And now what we would do here is we could solve only in mu and t, and then again solve only in lambda and t, and that gives you a new subset of scenarios in every iteration. And this is in fact very close to what the k-means algorithm does. So if you think about k-means algorithm, what you do is you've got plenty of points that you begin with. You start with some random solution, just like we do. And now you just repeat the two aspects of your clustering, which is for every point you decide to which cluster center do I belong, right? And once you've done that, you fix this assignment, and then you say, given this cluster, the subset of scenarios over here, what is the best point that covers all of these scenarios, right? So you may move your cluster center, and then you repeat. So you always have these two things, assigning your variables to the cluster centers, scenarios to the centers, and re-optimizing your centers. And we're doing the same thing here, except that every step now needs now requires us to solve an LP. Whereas in the k-means algorithm, you don't need any LPs. Okay, so the idea is similar. The concept is a bit more difficult, and that's why you need these more expensive tools to solve that. Okay, and what kind of scenarios could you get? So if you have like binary mus, you can still choose your subset of case scenarios from the convex hull. So these are the red crosses here. So the black dots are the scenarios that I would like to cover, and the red scenarios would be my approximate scenario set. And the blue crosses are then how much do I have to scale them up. Right? So the blue crosses indicate what is the quality of this clustering that I've done. And now, so you take something from the convex hull here, and in this case, you have to choose a subset of scenarios. But if you scale them up, you can use the convex combination of these. And in the last case, both are possible. So you choose something from the convex hull, and if you want to dominate everything else, you can choose something from the convex hull of these red points as well. So this will always give you the best approximation guarantee if you can actually solve that. And so if you look at the kind of quality of the bounds that you get out of this, so if I start with a very small problem, so just n items and n scenarios, I can then check if I aggregate down to 1, down to 2, down to 3, what is the approximation guarantee that I get before actually solving my problem. And you see that it is going down to 1 at the value of 10, because that's the case where you have the original problem essentially, right? And the other extreme point would be over here. You just have one scenario. So that gives you here for uniform data, a relatively high guarantee of something like 1.75. But if you have nicer data, like normally distributed data, you will also get better guarantees. Okay, and of course, your block descent method should give you the best guarantee in principle. But it's not just about the guarantee, right? You actually want to solve your problem and you want to get a good solution afterwards. So the guarantee is nice, but how good is the solution? And so what we've done here is we've clustered our scenarios down to K, And we've also run k-means. Okay. And now, how good is this clustering? Where to find out, what we did is we just sampled random X solutions. And to sample random X solutions, we literally just did in every Xi component uniform the random value between 0 and 1. So you can imagine this as a random direction. And then we calculated the worst case value according to our set and the actual worst case scenario according to the original set. And so this gives you like these kind of plots where here you have the actual objective value and here you have the estimate of your objective value. And if you didn't cluster anything, if you didn't change your problem at all, you would be perfectly on this diagonal because you don't have any error at all. And now you see you will always be below the diagonal because both our methods would choose something which is inside our set. So the worst case will be smaller. But that's not so bad, because if you think back to how big is my scenario size, you could multiply by 100 and you will be far above the line, but maybe it's still good because maybe you still get the same solution out of this. So we're not really interested in the absolute error here, not really in the distance to the black line, to the diagonal, but what we are actually interested in is something like how well does it correlate with each other. Right? So if you have a good correlation of your estimated objective value and the actual objective value, you can also hope for the same optimal solution, right? Or at least a same ranking of solutions. Now, the correlation is important. And so if you look at these plots from the perspective of correlation, so this is our approach, this is k-means, depending on the type of uncertainty set you use, sometimes it is reasonable. So this is just uniform data. This one down here is budgeted uncertainty scenarios. So this is all reasonable, but ours gives a tighter correlation. And now over here, what we've done here is we've introduced some outliers in our data. And now suddenly, if you've got outliers, the k-means algorithm starts to work noticeably less well, right? Because the outliers tend to like change the result of a k-means in a way that your points will follow these outliers, and maybe they are in the wrong direction. So with outliers, our method is much more precise. And what we did down here was we normalized our data. So we had uniformly random data and we normalized it back to the Euclidean sphere and added a little bit of noise. And again, so this is very hard to approximate because all scenarios are potentially relevant, but again, we get a much better correlation result than what you would get from k-means. Okay, and now let's look at an actual optimization problem. So I really like the selection problem. The selection problem just means given n items, choose p out of them. So the only constraint that you have is the sum of all your items adds up to p. Now, given 20 items, and we want to go down to 5 scenarios. So what you see here is the same plot that I started with on the first slide. It's just that we have logarithmic times now on the y-axis so that you can make a better comparison. So optimizing our problem in 100 scenarios becomes very hard. The continuous method of us, so our iterative method is a bit slower, but that's to be expected because we have to solve the LPs in every iteration. But the approximation guarantee, no, sorry, this is not the approximation guarantee, but this is the objective value of the solution that you get out of your problem is now very close to optimal. Right? So we're not talking about guarantees now, but the actual solution, if you don't solve with 100 scenarios, but instead with 5 scenarios only, means that you're within 8% of optimality at very, very small computation times. Okay, I'd also like to talk a little bit more about how to do that in 2-stage optimization. So I've still got 10 minutes, I think. Okay, so in 2-stage settings, the idea is that you...
Marc?
Yes, a question, please.
So can you go back to this? So in fact, what is the problem that you solve here? Is that shortest path problem?
No. This is this kind of selection thing. So this is one of my favorite problems.
Okay,
so sorry,
yeah,
I should have made this more explicit. So you choose something which is a binary.
Yeah.
And the constraint is that it has to add up to p, and p in this case is just n half. So given 50 items, choose 25 out of them.
Yeah, and so in fact with with a k is 5, for example, you solve it as a mixed integer programming problem. Why not?
So the resulting, yes, of course, I should have said that. Yes, I just plug into this standard epigraph reformulation, right? You've got a discrete set of 5 scenarios, you solve that, and I'm using, I think it was Cplex.
I see. And why does then it becomes more and more difficult when k increases? Because I see that there's a difference between
Yes.
case 1 and
Yes. That's a very good question. So the difficulty here of the yellow line, which is probably hard to read in this plot, is solely the difficulty of increasing the number of scenarios. So this is if you take n scenarios and you've got n on the x-axis, so more scenarios means a harder problem. Now, why do our own aggregated problems become harder? Because this is a sum of the aggregation time plus the solution time. And the solution time is always more or less the same because you always have 5 scenarios. But if you start out with more scenarios and you want to aggregate them down to 5, there's an increasing effort in the aggregation.
I see.
And of course, k-mean scales much better in the number of scenarios than our approach. That's clear.
Yeah, thanks.
Yeah. Okay, great. Okay, any other questions on the first part?
Yeah, maybe I have one. So you said you need this positivity of the scenarios.
Yes.
But in this first inequality, couldn't you just say, I take the average over all positive scenarios plus the one you choose, plus the maximum one, and then get the same? So in fact, your x hat is then the optimal solution in the average scenario only over the positive ones?
Well, okay. To be honest, I haven't thought about that. It might be that this is working, but this is only half the truth of why I didn't want non-negativity. I mean, of course, this estimate is only true if you have non-negativity. But another thing is that if you aggregate your scenarios down, you don't want to have combinatorial problems with negative costs, because that can make wreak havoc on the complexity of your problems. If you start out with shortest path, for example, you would really like to avoid negative costs. So that's why I just excluded them totally. But I could see that there's a possibility that you use these methods having non-negative costs as well. I'm not sure.
Yeah, because if your variables x are positive, then somehow only
the worst case is still the upper right corner. That's true.
Yeah, and the negatives one, the complete negatives one are anyway not useful. Okay, I don't know. Maybe.
Yeah, well, some scenarios will be a mix. That's a difficulty, right? It's not like you've got just completely negative ones and you just throw them away. But if you have sometimes negativity, I mean, that can do strange things to your average then.
Okay, thanks.
There's a question by Eric.
Yeah, I'm wondering, I was a bit late to the talk. I'm wondering, how do you solve the exact problem? Do you use some decomposition scheme, constraint
the exact problem you mean for the robust problem or the aggregation problem?
The problem with all the scenarios.
Okay. So no, I'm doing it in a very simple way. So I think that's similar to what Dick just asked. So what I do is essentially I just use where do I have some space? I'm just doing the epigraph reformulation. So I'm just saying minimize some variable z, and then z is larger than all the objective values for all I, right? And you've got something x and x. And now I just solve this as a mixed integer program as it is, without any added refinery in terms of decomposition or something.
Okay, thank you.
Yeah. Okay, thanks for the question, Eric. Okay, so let's talk a bit about how to do this in two-stage, and then we've got some more time for questions afterwards. So in two-stage, the kind of problem that I'm interested in is that you have an additional decision on top whether you want to buy something right now or later. And if you buy something now, you have given costs. So I'm indicating here with capital C. So you know capital C, and you can buy something now for these safe costs, or you wait. And if you wait, the adversary will choose a scenario, and after the adversary has revealed the scenario, you decide on the rest of your solution. So the kind of feasible solution that you would like to come out with in the end is something that the part you've bought in the first stage plus the part that you bought in the second stage is a complete solution. Right? So in this kind of selection setting, I want to get up to 25 items. In the first stage, I just buy 7. So there are 18 items remaining that I have to buy. Okay, now these kind of problems are very tricky to approximate because the average case doesn't work anymore. So here's a very small well-known problem. So let's say you can pick between two possible paths or two items or whatever. It doesn't matter much what kind of structure you have. You can buy an edge for 1 unit of costs. So that's independent of the scenario. So I buy something now, it costs 1, and that's it. But so the adversary has the choice between two different scenarios. In the one scenario, the upper edge is really expensive. And in the other scenario, the lower edge is really expensive. But always the other one is for free. So what is an optimal solution here? If the adversary has to choose either scenario 1 or scenario 2, well, I just wait. And whatever the adversary will throw at me, I would just pick the edge which is cheap. So the optimal objective value is that I don't buy anything in the first stage, and my objective value is 0. Now, if you look at any convex combination between these scenarios, right? Any convex combination will mean that you actually prefer to buy something in the first stage. Well, unless you're, well, if m is going to infinity, right? So if you do something like average case, it will be m half. So both of them will look expensive. So you rather buy in the first stage and you pay 1. Now, paying 1 in comparison to paying 0 is very bad from an approximation perspective, because that's like infinitely more than paying 0. So it doesn't give you an approximation guarantee. And it also shows that there's a big difference here between having the convex hull of your scenarios or actually the discrete scenarios themselves when you want to optimize. So we have to be much more careful when we want to aggregate. So it's not guaranteed that we actually just get something like an approximation in this case. But you can still use the result with 2 slight changes. So they look superficial, but they change the thing quite a lot. The first is that both of our alphas and betas should be at least 1. And that's because in our estimate, we have to take into account the first stage costs, which are also non-negative. And then because the beta is at least 1, this is actually going through. And another thing is, and this is perhaps more dramatic, is that once you've clustered down to one scenario, and the same thing will also work for multiple scenarios, I will show that in a second, is that you don't pick something from the convex hull of your original scenarios, but actually an original scenario as it is, and you have to dominate that. That has to dominate you. So, and this is clearly not fulfilled here if you take the average case. So if I take the average case of m half, then there is no scenario which dominates me by some factor beta, because the first scenario is m0, so I can't scale that up until it dominates me, and the other one the same. So that shows you why this doesn't work here. Okay, but if you can find something like that, then you have an alpha beta approximation. Okay, and again, we can plot this. And here you see it's not true anymore that you have straight lines as your level sets. Now it's not true anymore that you can just scale your costs up and down as far as you like, but instead you have level sets which are these strange polyhedra here, which tell you anything in this area will give you a certain approximation guarantee. And in that case, the approximation guarantee that with the best result is something in here, but that would be the same as over here. Okay, so here you can't just scale up and down as far as you like because of the first stage costs. Okay, and you can do the same thing again for multiple scenarios. So you can say for each of the original scenarios, you want to dominate that with something that you have. And each of the scenarios that you have, you must be able to dominate that with something of the original scenarios. So no convex hull here anymore. You're just looking at the pure scenarios themselves. Now, you can again formulate this as an optimization problem with very much the same variables as before, except that these mixing variables, the lambdas and mu's, are all now binary from the start, right? Previously, I had to assume them to be binary just so that I can solve that. But now they are already binary just to get some approximation guarantee. But because both are binary, I can actually reduce my P formulation using some reconsidering the variables and their meaning. So you can scale them down by quite a lot, and you get a small optimization problem. And this small optimization problem even includes these preprocessed values where you compare the ratios between two scenarios. So this is a much easier to solve problem now, which seems a bit like counterintuitive. You have a harder thing to approximate, and your approximation method is actually kind of easier than before. But that comes at the cost of having worse guarantees. So the same plot as before, 10 scenarios, 10 items, and I want to aggregate them down to 1, down to 2. The kind of guarantees that you get are now much higher than before, right? Down to one scenario gives an average guarantee of 4. Over here, you're still with a guarantee of 2 and so on for uniform data. And again, for normal data, it's a bit better. But the guarantees must be worse than before because the range of feasible solutions for your aggregation problem has been reduced. Now, this is a disadvantage, but it also has a good advantage, which is it's really quite fast to solve these problems. So here again, I'm using now a slightly different problem. I'm using a vertex cover problem to illustrate a 2-stage optimization problem. Now the optimal solution is going up. K-means is going up because there are larger scenario sets that you have to aggregate. But of course, K-means also depends on how many iterations do you want to run to reach the desired complexity, accuracy. And our IP, if you just plug it into the solver as it is actually quite fast. Right, so going from 140 scenarios down to 5 scenarios, less than a second. And that includes the solution time then. Okay, so this is very fast, but it comes at the price that the solution guarantee is not as great as before, let's say. And that's something that goes through most of the experiments that we've made. In quite many cases, you clearly beat K-means. You beat it from a theoretical perspective. I mean, you get a better approximation guarantee, but that doesn't necessarily mean that you get the better solutions. But sometimes you do, and at least you're really quite fast. Okay, so I'm already at the end of my talk, so let me briefly summarize. So everything I've talked about is how can you come from many scenarios down to few. And I completely do this independent of the actual optimization problem, which is below that, right? So when I did an aggregation for selection, I could use the same aggregation, say, for vertex cover. This is, I think, a nice feature because it means you can do this once and then you could run multiple problems with that. But of course, it also has a disadvantage, which is clearly I should be better if I use the actual problem structure, right? And this is something that we're currently working on and to include the problem structure in this approximation. And we've got some very promising first results. And another thing is, of course, a short advertisement. So I'd like to set out and collect some of these instances. So if you've got instance sets, I'd like to start collecting them and putting them online on a website. So currently there's not much here. Some instances we've generated ourselves, but I would like to reach out and collect some more instances so that we can compare our combinatorial or non-combinatorial robust optimization results there. Okay, so everything I've talked about is also available online in this eJob paper, and that brings me to the end. Thank you very much.